So a year ago, I was still running our small little company. I still have many slips of the tongue to call it CFS, but it's beginning to fade. But many people ask me what I'm doing now. I can tell you it's actually quite a big event when you leave the company behind. Because the company comes with a lot of headaches like finance, operations, and all kinds of things that is not so core to my interest. I now work mostly on storage architecture, primarily for the Lustre team, but also quite a lot with all the classes and teams and such. I continue to be extremely interested in meeting customers, so I talk to customers every week to learn about their requirements and so on. And I manage almost nothing anymore, so nobody reports to me or something like that, so I have I think at the moment, very privileged life of thinking about technology and storage. So in this presentation, I deliberately chose to do two things. A short part of the presentation, I want to try to convey to you some of the very exciting things that Sun is doing in storage. So this is a very Sun-biased perspective, I think I'm quite excited about it. But I also want to emphasize that we've always promised that Lustre will be a very neutral kind of piece of software that everybody can run, and most of the presentation is about Lustre and about future architecture. But this is not really a roadmap description. It's a description of things that we're working on because customers need them for one reason or another. So let's first look at Sun's vision on storage, and then switch over to Lustre. So when you look at the IT infrastructure in almost every organization at the moment, there are basically three kinds of environments that you encounter. One is the back office, where things like database servers, email servers, and those kind of things are running. There is HPC, and there is the web. And for a very long time, everybody believed that all the money in storage and computing in general was largely in the back office, but that is really beginning to change. For example, the fastest server growth is actually in HPC at the moment, and it's already consuming 95% of the servers. The web environments are, I think, going through a fascinating transition where they're beginning to use very sophisticated computation and storage use with things like macro use and so on. And so this is a whole new market that is emerging for interesting IT technology where some can play with hardware and software. So there have been tremendously many changes in all these environments. HPC, for example, has moved to clusters, but on a very big scale, everything has become open and industry standard. And so the things that I want to talk about here are how what has happened with servers in the past. So servers in the early part of the decade were really transformed from proprietary high-end servers like machines like Sparks and AIX machines and so on to an open platform with industry standard architecture. And we believe that this is now happening in storage, and we call it open storage, and it's worth to tell you what we think about that. So, open servers was something that was done to Sun. Sun was shipping Spark servers, and the introduction of powerful Intel and AMD machines was anything but easy for Sun. But in storage, it's perhaps the other way around. In storage, we're going to be seeing the same thing. So what I mean with open storage is, first of all, that software will all be open source. Yeah? I think that proprietary firmware for RAID controllers and so on, it will be there for a long time. Yeah, because we have a big customer base and want to move very fast. But it's not what we're looking at for the future. Just like Linux with open servers, things like OpenSolarity, ZFS, or equivalent Linux solutions will take open storage controllers in the future, and that's the software aspect. Similarly, the hardware is changing. The power of commodity processors with many cores, lower prices of RAM, and the revolution that is coming with Flash means that you can build storage devices as standard computers now, where there is no special rate controller hardware needed, no special architectures. You can combine an ordinary operating system with ordinary server hardware, and you can get very, very far. And so that is the combination of hardware and software that we call open storage in Sun. And the impact of this change in the market will be absolutely enormous. It will take some time, but it will be just as big as what came with Linux and open servers. In a certain sense, in networks, the same thing is quite likely to happen. The Open Fireworks Alliance, I think, is the best example of a software platform that is open and that is actually controlled by switches today. Yeah, this is also almost unprecedented in the past. This used to be very secretive proprietary software, and it's opening up. But that's in the very early stages, and I'm not going to talk about that. So for some, the ZFS file system is an extraordinarily central component in open storage. And let me tell you why we think that is and some of the things that we're doing with it. So what is ZFS? So in a certain sense, ZFS is just another disk file system, but it has many features that previously were either not available or only available in very specialized solutions. So for example, the end-to-end data integrity is something that's built into ZFS. ZFS will check everything it reads from the disk to check that it's still correct. So if there's bit rot, it will detect it. If the data was written with some redundancy, it will actually repair the data. And these were features that were available in rate controllers, or are still available in rate controllers. There are many good rate controllers that do these kind of checks and repairs. But the big difference here is now it's just a file system. Yeah, it's open source. You can run it on any piece of hardware, and the same kind of technology that previously came at a premium price is now openly available. ZFS is utterly scalable. It has it's very comfortable about file systems with trillions of files or petabytes of disks hanging off one server and so on. And these things, although in some cases they've been overcome, are in other cases still question problems. The administration of ZFS resembles what there are two ways to talk about it. In one way, you could say ZFS can be administered like an advanced RAID setup, like you get from EMC. You can add more disks to it, you can make volumes, you can replicate them, you can have different redundancy models. But you can also look at it differently. ZFS is basically doing with disks what DIMMs did to RAM. You don't manage DIMMs in your computer. If you feel you're short of memory, you just plunk a few more in. Yeah, and the same is what you can do with ZFS. If you have a requirement for more space, you just add more disks, and ZFS will manage it for you. ZFS has very, very good performance. Although in this meeting we might be talking about improving ZFS's performance, that is only because Lustre is extreme on performance. Yeah, there's nothing wrong with ZFS's performance, and yes, it does need some improvements, but it's a very, very powerful platform to build software with. So what can we really do with ZFS in the context of open storage? Because a file system by itself is not going to cut it. So, so this is just another summary of what components are that are in all file systems and rate controllers in ZFS. So, if you look at storage management, this is a huge market in which the industry is very big, and they have built absolutely fantastic systems now. If you look at rate controllers, they are very sophisticated and beautiful features. For example, redundancy, snapshots. You can replicate things. Yeah, EMC has things like SRDF and so on. You can monitor them very well. They can be managed. In many cases now, they're integrated with NAS exports. The plan of open storage is to simply replace these kind of proprietary solutions with things like Solaris plus ZFS. And we believe that this is the end of RAID controllers. If in the future a RAID controller will just be a large amount of disks with a good appropriate server for the purpose, and maybe some specialized pieces of hardware that also will be commodity by the time they come out. Things like flash drives and so on can help. So ZFS's features that I already mentioned, things like snapshots, like replication, like data repair, they are really a very good match for the high-end features that you previously found in enterprise storage management. So some can use ZFS for many other purposes. There's a product roadmap, of course, for storage software from Sun that includes things like NFS servers, ZIP servers, Lustre servers, iSCSI exports, fiber channel exports. Just think of ZFS as the backend for all of it, not just for one thing. It's going to be the central element of our open storage platform. And that's very exciting, yeah, because it is an open piece of software. It will probably get ported in one way or another, or done similarly on other operating systems. It's going to change the industry. Lustre adds another dimension to open storage, which is horizontal scaling. Yeah? And horizontal scaling is something that is, after many, many years, still very young. If you look at how many file systems you can buy that scale horizontally, particularly, for example, ZIP exports or so, or NFS exports, there aren't so many Lustre NFS exports that have good horizontal scaling. Yeah? And so there is another opportunity here to innovate for us. So as I said before, the reusability of ZFS is very central, and it has lots of enterprise goodies, and you will see a lot coming, I think, from us in the coming years. So in one of the developers' presentations, I found these few lines from Matrix, basically saying, it's coming, yeah, and there is going to be there's going to be a change in the storage industry that this time will not take some by surprise. Our hardware lineup with some version flash devices and so on, and I think maybe Henry Beckstein will tell you more about that tomorrow, together with this software, will position us very well to be one of the leaders in this change. I think the conceptual aspect of the change is such that many others will be doing the same thing, yeah, and that's important because otherwise it will not change the industry. Yeah, if it's one company doing it, it will be nice. If the whole world goes this way, it will be great. Good. So let me go and look at Lustre for a little while. So you've all heard our bragging that we run on 7 of the top 10 computers. It seems that I'm introducing all kinds of problems. Maybe this has nothing to do with that. My cell phone is in my pocket. It's starting to repeat. So we have. So in 1999 or so, this project was started, and I was one of the people that kind of stood up and say, "Wow, I don't think we can really do this. 100 gigabytes per second, 10,000 lines. It looks completely out there as impossible." But those things are in the bag now. Yeah, that's behind us, and we have to look at the next level of scalability and performance, and that's what much of the presentation is about. So I think all of you probably know what Lustre is, so I'll just go very quickly. Lustre is effectively a shared file system. It's a software-only solution. That's very important. Yeah, even though certain pieces of hardware might bring special benefits, like very fast networks and stuff like that, it's just software. The other important thing is, while Lustre was really developed by a company, it was, I think, an intense collaboration with the US government primarily, and then with some other users. And looking back at that, clearly we didn't know the domain, and the requirements all came from places like Livermore and India and Salomos and so on in the early phases, and then from many other labs soon afterwards. And it's actually quite a unique thing, because in most cases companies get started by venture capital and they have some big vision and they make their own decisions. I think we didn't really make our own decisions. We chose the best architecture to meet what the customer wanted. And it's very gratifying to see that when you look at these 7 systems that run Lustre today in the top 10 in the world, there are, I think, 5 or 6 different hardware vendors in it. So it's really seen some uptake. But it is a very small market. Yeah, it is a market of extreme storage. So this is also how Sun is positioning Lustre. We don't really see Lustre as the right system to run Oracle databases or something like that, or email servers. Even though it may work well, that's just not the focus at all. The focus is extreme storage. Now, in extreme storage, the most important thing is horizontal scaling, meaning you use many, many servers to build very fast and very big file systems, not just one server. And what we will see in this presentation is that extreme storage is beginning to happen on a big scale outside of HPC. And this is quite exciting. It will help the HPC aspects of it, but it will also lead to new uses of clusters. So the kind of deployments where we have Lustre is mostly in the extremely large clusters, all very well known, I think. And one of the big strengths there, really, I think, was the modifiability of the system. Yeah, in almost all cases, when we were presented with the next big computer, things did break. They didn't break for very long, and they didn't break in a way that was so fundamental that we couldn't fix it, but things had to be changed. And I think the best example of those changes is still large Livermore and something like that. Yeah, although many others will be following. I think, for example, at the moment, Oak Ridge has a very big computer coming in there, introducing many changes. But the modifiability at the high end is very, very important. And the modifiability has been extremely difficult for us to keep up with. As Eric Barton explained, the primary concern now is about quality, and that you pay a price if you want to make big changes quickly because you damage quality. So this modifiability is at risk at the moment, and we will work very hard to keep it. In medium and large clusters, we just ship it. There are many, many Lustre installations where practically no changes are made, and I'm in a way very proud to report that I think when Lustre was deployed on the TAC system in Texas, that we only had to fix one bug. There were no changes made for TAC, and that is in a way a very good sign because it means that even though TAC is one of the biggest computer in the world, it's pretty working pretty well in many situations now. The very exciting new things are other kinds of very large-scale data centers where many clusters are being used typically in the wide area. And the most important examples that I have are ISPs and the Department of Defense. The ISPs, we are working with maybe 5 or 10 ISPs now that are interested in using Lustre in content distribution networks, for example. And these are very different kinds of installations where maybe there are not so many servers, but there are petabytes of data. They replicate it to multiple places in the world. And one of the funny things is that there is one major ISP that doesn't have a Lustre support contract, and you are likely to sometimes pull a movie on your laptop that are ultimately stored in Lustre because they have just put it in production and it's apparently working. Yeah, yet these are early examples, and I think a lot of work is to make it more solid. We were introduced to the Department of Defense a few years ago in the Navy Research Lab, where there's a study going on for large data management in the Department of Defense. And large data management in the Department of Defense is really very interesting because it reminds you of James Bond and so on. And so they have absolutely massive intake of data from things like satellites and drones and so on. And the numbers are truly staggering. If you search seriously on the web, you can find these kind of presentations. They're talking yottabytes by the middle of the next decade. And yotta is so large, I don't even know what the exponent is exactly, but it's 1 million zettabytes. Yeah, so it's really, and the fact that they are after this is reflected by operational things today. I've heard that most of the data is thrown away today because they just can't store it at all. So there you go. By the way, how is this data produced? It's actually extremely simple. There are planes flying around taking lots of extremely high resolution photographs very, very fast, and cameras are cheap, so they hang 10 or 20 cameras on a little drone, and there are thousands of drones, and they keep flying. And you can just imagine, and we never throw something away. You don't have to, of course. So what do you do with that data? First of all, the military organization is always concerned about what they call COOP, continuity of operations. Yeah, so if a bomb hits one site, they want to be able to have another one. And so they need multiple copies of this stuff. Replication of petabytes of data is not particularly easy, and this is something we will be talking about in a little while. We found some nice new algorithms, quite simple ones, but quite promising ones to do this. Another thing is that this needs to be searched. Yeah, this data is not really overseeable, and so we need to be. Many organizations have their own data mining. So what we're not doing is what WinFS was planning to do in Microsoft, integrate search into the file system or stuff like that. That I think is not so practical, maybe. But like the Department of Defense has a huge infrastructure with Oracle databases to do data mining. And we can help that Oracle database tremendously if we just tell it, here are the new files, so that it doesn't have to crawl the whole file system. Yeah, or these files are changed, these files are removed, so that it can update its indexes very fast. So searching is very important. And then the final aspect is a very interesting data management aspect. So suppose some spook at the NSA is finding out that Peter Brown has to be captured, and they find a couple hundred files with pictures of me and my car and so on. So how do you manage that? So that's some kind of a search result which you now have to send to James Bond so that he knows who to shoot at. And this is a very difficult problem, yeah, because there will be hundreds and hundreds of different search results that somehow need to be managed and need to be kept up to date. I think that these data management problems are very, very interesting. And what surprised me is that while the most interesting story is perhaps the Department of Defense story, when you talk to banks or you talk to large document management organizations, it's actually rather similar. Yeah, so I think we're on to something here that the industry needs, for which, by the way, everybody agrees there's not really a good solution today. Yeah, there are bits and pieces, but it's definitely not solved. This Lustre picture, can we skip it? Or probably skip it. So this is perhaps just a good idea to just remind you how Lustre works. So there are many, many clients in Lustre, and then there are metadata servers. I just drew one metadata server. The future version of Lustre will have more than one. And there are object storage servers. So the file tree is all stored on the metadata server. So we have one or more servers that contain the tree, but they don't contain the file data. And if you were to look inside there, you would basically just see a large directory tree like you might find on your laptop with no file data. File data is stored on those servers. Typically, we call them object storage servers. With hindsight, we should have called them I/O servers or Scribe servers or something like that. And so the capacity of the file system is almost entirely in the green servers because that's where the file data is. And if you're wondering how big the metadata server is, it's on the order of a percent or something like that. So if you have a petabyte of file space, you only have 10 terabytes of metadata, which is just a shell. It used to be a lot of things, so it's not like that. So the layout of files is interesting in Lustre. So you can, in simple cases, you can just put a file on one of your object storage servers and leave the whole file data there. So that's very simple. But to get high bandwidth, the files are striped. And so here's an example of files that are striped over 3 servers. And this means that you can read and write to all these servers at the same time, so you can get more bandwidth on the file system. You can also store larger files. You may be curious to hear that one of our customers is interested in storing a file that is over 100 terabytes, one single file. So that's kind of difficult to store on one disk, and even very difficult to store on a RAID array. You need a huge rack of disks, and much better to use multiple servers. By the way, I have no idea what this file exactly contains. It's probably some kind of academic experiment that will change up here. So, looking at where we need to be moving with Lustre, given where we are now, I put up the following slide with kind of a list of elements that are important. And product quality absolutely has to be at the top of the list. And so major work is needed, even though I think our product quality has improved very dramatically over the last few years. It's still, there's always room for further improvement. Yeah, it can't be good enough product quality. So this is very important. It's when I speak about product quality, I think we need to think about that very broadly, not just saying we need to fix bugs, but also we need to make sure that our code remains very structured and well organized so that we can move forward with these new features. Because as I said, there's a threat when quality comes in that everything else slows down. And I believe that Eric Barton is thinking very hard how to overcome that and bring more structure. Performance fixes will absolutely never stop. Even though in many, many cases performance is good, there are always new applications and problematic scenarios for which more changes are needed. I have to say that the difficulty of making performance improvements is now very low. It's just routine work. It's a lot of work because quality is hard. So doing software correctly is hard, but it's not something that is challenging architecturally anymore. We know the tricks. But by the way, I keep waiting for the moment that we get, for example, a good reputation for small file performance, because our small file performance is actually really very good. It's what a lot of people tell me, but a rumor has it that it isn't. So it will be interesting to see when I turn on that. The HPC scalability, while it continues to be a challenge, I think at the moment the challenge is reducing. So for a short time, the number of nodes was shooting up very, very fast. So we, for example, had the Red Storm machine where every client had one core to compute. Yeah, and we have like 30,000 cores or something, or 15,000 cores in the beginning. That's changing very fast. At the moment, we're beginning to look at machines that approach 100 cores. And so that means that the number of clients is much, much smaller. And so that helps us with that kind of scalability. On the other hand, it brings in another issue, namely that we need to be very multi-threaded on these clients with many cores. Yeah, so there's always some new problem, as I said before, to help. The most important enhancement, I think, for performance in Lustre is something that we call a network request scheduler. It's very, very strange that this hasn't been done in the file systems before. I think there's probably databases have it in their transaction monitors or have had it for many, many years. But what we really want to be doing when you have thousands of clients writing to a large file, for example, you might as well order all those writes so that the I/O just goes sequentially into the file. Yeah, why on earth would we follow a model from the early 80s that says first request, first execution, second request, next execution? Yeah, that doesn't make much sense. So we're going to be looking at all the requests and making them better to get performance improvements and basically make our life easier. Yeah? And I think that this is a change that will probably be coming either very late this year or otherwise next year. The wide area features, I have many slides about that, so I'm going to not say too much about that. Broad adoption for Lustre is perhaps not so important. Yeah, our attendance here keeps doubling, and doubling is always good because at some point the numbers get big very fast. We are focused on extreme storage. We're not trying to conquer the world here with a universal file system for everything. However, there are opportunities in Sun, for example, to let the PNFS effort in Sun leverage Lustre. I mean, we have extremely good servers, yeah, and why not put that together? So I will be telling you a little bit about that. I think this is something that you've heard about. We're going to be using the DMU as the backend file system in the future. So the ext3 file system is going to slowly be on the way out, and this for 2 or 3 reasons. One is scalability. The demands for trillions of file systems are very difficult to meet with the old architecture. But the integrity of data that I mentioned earlier is just so fundamental. We do need a different file system. I think Eric was very modest. I want to just say that there is a huge amount of good news on the DMU work with Lustre. The performance problems are beginning to look very tractable, and I'm very optimistic now that the choices we made will prove to be very good choices. To talk a bit about PNFS, so parallel NFS is coming. There are a couple of interesting ways that Lustre can play with PNFS. So on Linux, for example, the PNFS servers were simply layered on cluster file systems. So anybody who has a cluster file system can build a PNFS server by running the PNFS servers in the Linux kernel with a small plugin, and we wrote such a plugin for Lustre. We actually participated in a Bakeathon. This is a new thing for us to do anything except pay attention to our customers. And it worked. I also heard that the Linux PNFS servers were anything but stable and good at the moment. Yeah, they were very flaky, but it at least worked. However, there are longer-term possibilities here that are much more interesting. And for some, PNFS is clearly something that needs to be stated in the product. It's an industry standard. We'll probably find very wide adoption in commercial HPC. And why not let the Lustre servers do both PNFS and Lustre? Yeah, and let's look at some pictures how that might work. Yeah, so on the left side here, you see how the Linux solution will do it, which, by the way, is, in my opinion, an extremely good solution because it's of the simplicity. You have to say, I just layer one server on top of another. This is the way computer engineering, software engineering has always worked very well. There's nothing wrong with that. But the more intimate idea of serving directly has also advantages. For example, maybe the Lustre client layer isn't sufficiently robust or performant. And if you have direct servers exporting from the Lustre backend, that might help. So this is something that we some would like to do, and this is actually something that customers ask first. Maybe customers say, "Boy, you're building all these different file systems. Can you rein them in a little bit?" And I can't say we will do it, but we are deep into looking at the architecture now because we really think it's possible to let the PNFS product for Sun and the Lustre product just use the same servers. Yeah, and so maybe it can run at the same time. It will certainly use the same disk formats. And if you start thinking about everything else that's coming, there's going to be a lot of data management stuff coming in the future. HSM, replications, snapshots. If you do that for one set of servers and you get it for free for the other, yeah, that makes a lot of sense. So that is something that I think we're very interested in. The next thing I want to talk about is what we call flash cache. So there is a revolution coming with flash storage. And I think slowly the word is really getting out. So many people know that flash storage runs in your iPod, and there are now flash disks for laptops and so on. It is in fact possible to make flash storage devices in many different form factors and to get absolutely unbelievable bandwidth on it, as well as I/O operations. And the interesting thing is that the cost of this flash storage is going to be a small fraction of the cost of RAM of the same capacity. And for high-performance computing, that leads to a very interesting scenario, because in high-performance computing, the typical I/O pattern is that a computation is proceeding in the cluster, and it needs to be dumped to storage. And that dump might be for a checkpoint, that dump might be because we have the final results, yeah, but it's always, in most cases, it's the data in memory that needs to be dumped out as quickly as possible so that the next computation can start. And so the typical kind of goal that people have been talking about is to write that data out in maybe 5 minutes or something like that, and then proceed with the next job and do another run at dumping data an hour later or something like that. Now the problem is that to do that dump in 5 minutes, you need more and more disk spindles, yeah, because the RAM is growing very fast, the disk bandwidths are not growing very fast, but the flash bandwidth is going very, very fast. And given what I just told you about the economics, what you could do is build a small flash cache that, and with small, I mean not so small. It would be about the same size as the RAM in your cluster, so that you can do these memory dumps to flash. And you can take an hour time after you do the dump to flash to bring it to disk. So you could basically be looking at disk bandwidths that are maybe 5 to 10 times lower than what you're looking at the moment with disk storage, and absorb the data into the flash cache first. So this is going to be a reality. I don't think I'm allowed to make detailed product announcements. So there are flash boxes coming that have bandwidth for 1 U that compares with the bandwidth of 2 racks of disks. Yeah, so you can also think about power consumption here, space, and so on. Yeah, so with a couple of flash boxes that have some terabytes of flash in them, you will be able to get unbelievable bandwidth to build a flash cache. Yeah? And the idea is that Lustre will use that. And when the our first model of the flash cache, we're just going to try what I've drawn here. We write everything to flash, and so that it gets into that flash storage as fast as possible, and then we drain it out to the traditional OSSs with disks at a reasonable speed. If somebody wants to read the data, we will always read it back from the disk. Yeah, we don't necessarily see this as a read cache at the moment. We just want to get this I/O problem solved. Many people have been talking about the next generation of machines called exascale machines. There have been some workshops and so on, and I think that this offers some promise there, and nothing else seemed to work. Yeah, we were looking at 1 million disk drives for an exascale machine a year ago. This looks much, much better. And it's going to be affordable. And it's actually the first revolution in storage devices since the 70s. I think this is the first time the damn spindle can stop. Yeah, we can write to flash. So this is very, very exciting. Maybe there's no extremely particular reason why not to do that. This is very flexible. The fact that the flash storage is separate means you can just add it and you can grow it independently and so on. So we did like the fact that it would be very network central. Yeah, and so these flash storage will, by the way, just be ordinary object storage servers. Yeah, they will be attached with probably like 4 times QDR in baseband or something like that to get something like 10 gigabytes per second per unit. Yeah, and so we thought this was a flexible solution. I want to emphasize that with this flash storage coming, and just flipping back to what Sun is doing, I want to say 2 things. First of all, we are doing nothing that other vendors cannot do. Yeah, so we're doing open interfaces. These are just storage devices with flash. Anybody else who builds these storage devices can use Lustre in the same way. Yeah, we are not building special versions of Lustre for Sun or something like that. Yeah, we might be leaving the pack. Yeah, but that's the only thing. Flash is going to be universally available for many, many good things. And so, of course, we are going to be using Flash inside the ZFS file system for journals, for caches, and for all kinds of other purposes like MIUs and whatever. Yeah, so there's no question that we can use it for multiple purposes, but this, I think, is a pretty special HPC application. Yeah, that is worth calling out at this point. Good. A write-back cache is something that we've long talked about, and the big issue with network file systems is that unlike disk file systems, they don't make their updates in memory for the most part. Yeah, network file systems always go to the server and say, give me a file identifier, give me this attribute, or do something over the network, and the latency is absolutely enormous. If you compare going over the network to doing something on the local machine, it's a huge difference. So the Lustre write-back cache is something that we've been working towards for years already. There are many, many changes in Lustre now as the foundation for this. this will be, I think, perhaps the first file system that has a complete metadata write-back cache. And so you can do everything in memory without talking to the server. You will still have to occasionally talk to the server. Like you would tell the server, hey, I want to create another 1,000,000 files. Can I get a set of file identifiers? Yeah, but that's acceptable. Yeah, what's not acceptable is to say, hey, I want to create a file. Hey, I want to create a file. Yeah, we want to batch the communication with servers, both for before the creations and after. There are many key elements in the design which we can maybe talk about tonight or so over some food or party or something, but it's a very technical thing, it's very interesting. One of the big puzzles that we have is we are going to be having clustered metadata servers next year, and how do we synchronize these caches to multiple metadata servers? This turned out to be quite difficult, but I think we found a good solution for that. So the uses of the write-back cache are actually quite many. This is a very valuable element to have. In high-performance computing, I think the most important purpose is perhaps that of I/O forwarding. I have a picture of that in the next slide, I think. Yeah. So if you have very, very large clusters, like for example the LUG machine in Livermore, it has an I/O mechanism which is not strictly client-server. It has a hop in the middle. And the compute nodes do what's called I/O forwarding to an I/O server, or a forwarding server, and then the forwarding servers are going to the file servers. And this is just to do with scale. Yeah, and at Livermore, I think it's now 200,000 of these lines on the left or something like that. That's going to be a large number that talk directly to the servers. Now, the pleasant thing is that if the forwarding server is a write-back cache server, that means that all the traffic between the compute nodes and the forwarding server can go very, very fast, because that forwarding server doesn't create a bottleneck at the next level. Yeah, and so this is, I think, an important application of the write-back cache in HPC. Quite generally speaking, in extremely large clusters, a write-back cache is a very good thing to have. So you have a pile of changes. It's very advantageous if you can make a last-minute decision. Where do I send those changes? Yeah, maybe there is some part of the server that's suddenly idle, and so on. And so having a write-back cache allows you much better resource than you can do without. The WAN is obvious. With the write-back cache, the latency is gone. Yeah, and latency on the WAN is actually very important for metadata updates. Yeah, for file I/O it's maybe okay because there are caches already, but for metadata updates it's very important. I think we're getting a presentation this afternoon about the HPCS project, and John is probably going to tell you about some of the numbers that people want to achieve there. They want to see file creations, small file creations on a single node, I think on the order of like 30,000 or so per second, small files completely open with flows. You may want to stop for a moment and ask what you can do today. If you have a very good machine, you might do 1,000. Yeah, so we're talking between 1 and 2 orders of magnitude of improvements here. And to a certain extent, some hardware will help you to build a good machine, but software will definitely have to help you innovate the network latency. So that's another good motivation to build a write-back cache. The next few topics are all about things like data migration and replication. So data migration has so many uses. There's almost no end to it. The moment you think you finish something, there's another idea how to use it. First of all, when we change from the Lustre Linux disk file system to CFS servers, we want to migrate the data. People will not accept it, that they have to buy a new server or something like that. So that's a good goal to have migration. Space rebalancing. So funnily enough, things get out of balance. Sometimes some servers get full. There are too many hot files on some servers by accident, and you need a mechanism to migrate this. Emptying servers is still one of the favorite storage management things that everybody wants to do. Why would you want to keep these old servers with 100 gigabyte disks? Yeah, and those kind of things. They just consume far too much power. HSM requires file migration, caches and replicas requires migration. So migration is so central, you need it for just about all storage management. So here's the picture of migration that is being worked on, and this is something that is actually not being done by us, although we've helped a little with the architecture, and the people at CDA are working on this. So the model that we've chosen for data migration is one that allows you to restripe. Yeah, so it's not a good idea to think, oh, I'll buy a new server and we'll copy everything from the old server to the new server. No. You have 20 servers now and you're buying 8 new servers. Yeah, it's that kind of picture. So you need to reorganize your data as you are migrating. Yeah, and so that's called restriping. And that makes it much more complicated because it means that instead of moving things from one server to another server, which looks like a relatively simple thing to do, you're moving it from so many servers to yet another set of servers, and you have to manage this all. So we have a coordinator in the cluster that keeps an eye on all the migration activities that are happening. So when you want to migrate something, you tell the coordinator, move these files to another set of servers. And then we have agents, data moving agents, that will pull the data or push the data from one set of servers to another set of servers. Very, very important, and these are the kind of things that you don't really see when you run Lustre, but that are very much part of our work. The new metadata servers are in fact layered on the object servers. And this is very, very pertinent to migration because it allows us to migrate metadata if we can just migrate data. Yeah, if we can migrate objects, we can also migrate the metadata because of the layering. So the Lustre, I don't know what the number is, 1.10 or 2.0 server will come out with a metadata server that's actually based on the same object devices that we use for file storage, and the migration mechanism will be the same between them. Yes. And there are various ways, by the way, to handle hot files. So the ultimate solution is that I/O can be happening while you're moving. Yeah? But there are other solutions that are probably acceptable that might come out first. For example, you might start migration, but you might simply stop it if somebody is opening the file, so that the opening, the I/O to the file proceeds, yeah, and you just retry the migration later on, yeah, and those things are definitely being looked at. There are also, by the way, cases where you need to abort it for semantic reasons. For example, if you're putting a file in the HSM and it starts being written to, it's probably no real reason to continue to write at that moment. Yet you might want to wait until it's closed and things like that. Maybe not always. But so this, what I just showed you here, is very internal to Lustre. Yeah? I'm showing you I'm moving from one pool of devices to another pool of devices. What the people that I talked about earlier are doing is quite different. They have different separate file systems, large file systems that are completely separate devices, separate servers, and so on. And they just want to have a general purpose replication of file systems. So this is really what we would call the rsync problem. The only problem is that if you run rsync on a petabyte file system, it will take a very, very long time. Yeah, and this is where we're making some changes. So one of the things that we are adding to Lustre is a change log that allows you to quickly see which files you need to change. Now, this actually turned out to be quite a puzzle to do this right, and we have to actually think mathematically and so on, which our old brains are maybe not so used to. But for replication to work on live file systems, you have to be very, very careful because files might be changing. You might think you have to sync the file, and then it has been renamed in the meantime, and you forgot to sync it. And one of the rules we wanted, of course, is if we promise we synchronize the file system, we replicate it, then we will replicate it in its entirety. We will not forget the file. So we had to work quite hard between the change log and some special path operations to work on live file systems. So you can migrate live file systems and it will remain correct. Another important thing is no scanning ever. Yeah, I think scanning is evil at large scale, and immediate resume is very important. Many of these rsync operations that you might even do at home with your photos or your music, they will fail because of some kind of flaky network, and you will just start it again. Yeah, and starting again is not an option at this scale. It needs to resume where it left off. Finally, and it's just one word, and it's a big thing, how do you do it in parallel? Yeah, it's not possible, really, to think that you have a few hundred servers making up a very large file system, and you say, oh, I'll use a Lustre client and copy it all over from one set of servers to another. It just won't scale. The other client will not nearly have the appropriate bandwidth. So the parallelization of things like replications and synchronization is very, very important. The initial solution that we will come up with is roughly as follows, that the namespace changes, meaning adding and removing names and renaming files. So this is just purely the layout of the tree that initially we will do with one client. It is actually very difficult to parallelize that because of dependencies. There is a possibility of parallelizing, but it's not very simple. But then everything else can be parallelized, like moving data, moving attributes, and so on. Yeah, and that's at least a very good start to get off the ground into parallelizing it. By the way, the change log has, and this replication mechanism has many, many other users. For example, once you have the change log, you can feed it into the Oracle databases. Yeah, they get the right information. But you can do other things. You can say, oh, I have objects sitting here for these files. Let me make some copies of the objects and replicate them out. Yeah, and so we can do some simple models of things like server network striping with the same mechanisms. About this project, by the way, I'm particularly excited because it's being worked on very hard with the customer that is sort of jumping to try the bits and pieces. And I think there is some hope that at the end of this year we have a good data or something like that, but it's still really coming. But just a few more slides, caches and proxies. So there are many, many forms of caches, and let me just show you a few. So HSM is clearly one form of a cache, yeah, a very big cache. But another interesting issue that's coming up all the time is what you could call BitTorrent style reading. Yeah? So there are many, many computer applications that all read the same startup file, and this can be, Lustre is not very good at the moment. I think it reads the file again and again from disk. And if you have a perfect server where the disk bandwidth equals the network bandwidth and so on, it's maybe not so bad, yeah, but we can do massively better. The other very important case is like area caches. Yeah, there are many cases where people do not want to pull files over the network all the time. Yeah, they want to have some kind of collection built up dynamically fast and relatively nearby. So there are many, many technical elements in it that I don't want to go in. I would like to talk for a moment about the collaborative cache, which, by the way, we, I think, prototyped in 2003 for the path forward contract. We had so many of these ideas have been around for a long time, but they've all gotten pushed back again and again and again for basic product quality. But I think we're now at the point that we can really move forward with them. So one model of collaborative reading is to say, well, the first few clients can read this file from the first object storage server, but when that object storage server gets kind of busy, it tells the next client, listen, read that file from the next object storage server. Yeah, and the next object storage server could become a cache, dynamically become a cache for the file. So you pick up another hop, yeah, but you only have to move the file one time to the OSS, and then you have a new server to maybe serve another 100 clients or 1,000 clients, whatever is appropriate. So this is one model. Another model would be to do this peer-to-peer, which is not very different, in fact, from what I've drawn. And then you really have the kind of BitTorrent model. Many people don't like their compute nodes being used as file servers, but that's only in the HPC world. If you go to the world of Web 2, where things like Hadoop and the Google file system run, they don't want to do anything else. Yeah, they have no separate clients at all. They only have these cool things that are both serving and clients. So it just depends on what we're doing. The bigger picture of proxy clusters is something I've drawn here, that there would be a group of Lustre servers that would perhaps be either read-only or read-write and have data available. There's many management aspects to this, like what data do we actually replicate there, or is this purely done on a cache-based basis, and so on. But I think our customers will be telling us. I want to mention, by the way, that the caches and proxies are we spend quite a bit of time on the design of them, but we are not actively building them. The replication, on the other hand, is really coming, and the migration is really coming. HSM and space balancing and so on, those are very, very important things to have. This is, I think, the next level, and it's probably really more complicated. I have a feeling that this is my last slide.